Hello, and welcome to the final part of the studio build series, where we'll be having a look at the speakers. All the speakers for the Atmos system were specifically designed for this room and built by me over the course of several years. Let's have a look at how it all started. The journey to the main stereo speakers started in 2017, when I bought a pair of speakers built by Ken Gores. They were prototypes, which he let me use for a temporary setup while I was in LA. Coincidentally, I was in the market for new speakers, so during that trip I went around and listened to everything I could, which was around 300 different speakers. I kept being disappointed as nothing stood up to the ones that Ken had set up for me, and I eventually asked Ken if he'd be willing to sell me those prototypes. Those speakers consisted of a 10-inch sub on the back, a 10-inch mid, and a compression driver in an asymmetrical waveguide. The DSP was handled by a modified DEX unit, and then over the years I went through a couple different amps like Hypex, Parasound, and designs from Nelson Pass. The concept of the asymmetrical waveguide was originally developed by D.B. Keel working at JBL in the 80s. It was called defined directivity. This design approach gives you a wider sweet spot by having the speaker project more sound to the other side of the room. In other words, if you move towards the left side of the room, the left speaker actually gets quieter, while the right speaker gets louder, so you can still perceive the stereo image instead of it collapsing into the left speaker. Unfortunately, controlling directivity down to low frequencies requires very large waveguides, so JBL mainly made these for the Japanese market, where customers generally don't mind giant speakers, but it never caught on outside of that. A couple of pro audio companies resurrected the approach and applied it to some PA speakers to throw more sound towards more distant listeners, while not blasting listeners that are close to the speaker. The speakers from Ken were great, but their output power was a little limited by only having the 10-inch subs, and I wanted to see what it would be like to try making an improved version of them. Ken helped me work out a bigger and better design, which used 15-inch subs, a 12-inch mid, and a larger waveguide using a better compression driver, which allowed the directivity control to be extended down to a lower frequency. This may seem like a lot for a smaller room, but larger drivers allow for lower excursion, which reduces distortion and creates an effortless quality. There's no such thing as a sub being too large for a room. Originally, they were ported, but I made them sealed, which ends up significantly improving how the speakers sound in the entire range of the sub. I designed and 3D printed the new waveguides for these new speakers. Once I got a CNC router, I then made a slightly improved version out of MDF, which was a lot heavier and less resonant. When planning out this new room, I wanted to stay along the same lines and design a bigger system that would extend that asymmetrical directivity control down to lower frequencies. At the same time, I started exploring different speaker design approaches. Speaker design is all about trade-offs, and it's physically impossible to have the perfect speaker. I wanted to learn what made different speakers great and what the trade-offs were. I started out by studying pretty much all the top speakers on the pro audio and hi-fi market. I had only heard some of them myself, but others I knew were well regarded. My next step was to get some of the best drivers around and start experimenting. The subs I use are from Acoustic Elegance, and they can easily extend to 1K, but I knew I wanted to cross them at below 150 Hz, as I find low crossover points to be advantageous. All the designs I was playing with were designed to take over from there and integrate with these subs. I tried every combination of woofers, mid-domes, tweeters, ribbons, AMTs, compression drivers, and planar magnetic drivers, in all sorts of configurations with things like waveguides and open baffle designs. I won't get into waveguide and horn design here, but there are many different ways to approach them and design them with different trade-offs. So one of the things I was experimenting was with different horn designs. I bought the best ones on the market and then 3D printed others, giving me around 10 completely different designs to test. Overall, the COS waveguide design gave me the most neutral sound, but I found the mostly straight walls to introduce some problems, so the asymmetrical waveguides I ultimately designed are loosely based on an asymmetrical COS waveguide with slightly more curved walls. All of my testing led me to 5 completely different design approaches, each with their own advantages and trade-offs. I decided to build this particular design as the only way it can work is being integrated into the wall, so this is the only way I could test to see how well it worked, and was also the next step in that design path of the speakers I was currently using. I'm still in the process of testing out the other designs, which feature things like the Bleesma beryllium mid-dome and tweeters, with Purify woofers, as well as a unique cardioid approach, which gives me the benefit of open baffle speakers without the drawbacks of having a dipole radiating pattern. I may eventually end up replacing the center section of the main speakers with one of these designs, and the center section is designed to be easily swappable. One of the things I found in my testing was there was something magical to having a single driver covering everything from 500 Hz and up. This led me to using a 1.4-inch compression driver with a waveguide designed to go down to around 500 Hz. I could have potentially gotten lower by using a 2-inch compression driver, but that larger throat size limits its ability to play the top end cleanly. I'm using beryllium compression drivers, which allows it to make it up to 20K. Other materials aren't able to do that with a compression driver this size. This driver has a 4-inch beryllium dome in it. For the mid, I was previously using a 12-inch mid. I decided to switch to using two 8-inch mids so that the distance between the drivers was smaller, and that improves how the drivers integrate with each other. This also helps with designing the waveguide on the mids, which extends down the asymmetrical directivity. The cabinet for the mid section is 12 cubic feet, which is quite a bit, especially considering that they only play down to 120 Hz. In my testing, I found that open baffle designs have a number of advantages with making drivers sound natural and lowering distortion. This comes from not having an air spring constraining the driver, like with most speakers. Unfortunately, you get a number of problems from having that rear radiating wave on the back of the driver playing into the room. The solution to this is what's called infinite baffle, where theoretically you have an infinitely large baffle separating two infinitely large spaces, so that the driver isn't constrained by an air spring on either side, and you don't get the rear wave going into your room. Of course, having a real infinite baffle system is physically impossible, so the next best thing is to have the cabinets be as large as possible, and there are some ways to calculate how large they need to behave similarly to a truly infinite baffle system. The mids do achieve this, but the subs, which are in 8 cubic foot enclosures, don't quite. That was as large as I could make those cabinets. Theoretically, I'd need about 120 cubic feet for each sub driver, which is about the total size of the speakers on both sides of the room. For designing the waveguides, I first created my own simulation program, which allowed me to see how two speakers would add up in a room. First, we can see how a regular speaker would sum around the room. The goal is to have the darker area, where the difference in output is 0. That means the signal from the left and the right speakers are coming at you at the same level. We can then look at what you get with the asymmetrical directivity, and you can see how much more of a darker area we get, where the two speakers would be more balanced. This gave me the dispersion pattern I should aim for. I then used Fusion 360 to start modeling different designs, and used a program called Acrobat to simulate these waveguides and see how close they got me to the directivity I was after. From there, it was just a matter of CNCing the waveguides, as well as 3D printing some parts to make it possible to attach the drivers onto the waveguides. There were countless parts to designing these speakers, and I know I've jumped around and skipped over many details, so let's go back to the general design of the speakers. These speakers use triangular cabinets, which are effectively flush mount without actually touching the walls. Flush mounting eliminates the interaction between the speaker and the front wall, which creates a dip in the response, and that's actually just one of the symptoms of having all of the low-end energy bouncing off the wall and reaching you at a later point in time, affecting the entire bottom end. Flush mounting also gives you more output power in the bottom end, since all the sound is pushed forward instead of some of it first traveling back and then towards you. On each side, I have 4 15-inch subs. The inner ones are used for stereo, and the outer ones are used for the LFE channel. The subs for stereo are sealed, which gives the best transient response, and allows me to extend them as low as I want. They're currently going down to 14 Hz. With my regular mastering work, you can't see the woofers move at all, but with some theatrical content, they do get pushed to their limit, which is why I didn't extend them lower. The LFE subs are ported and tuned to 14 Hz. These have to be ported based on the output power required for Atmos. There are 4 of these 15-inch subs for the LFE channel, with 2 on each side, and if I wanted to make them sealed, then I need to at least double that and have 8 15-inch woofers. If I had designed these to only go down to 30 Hz, like most subs, then it would have been easy and I wouldn't need this many subs, but getting that last bottom octave requires a lot of air movement. The way I design ports is different from what you see on most speakers, as I make sure the air velocity will always be low and the port won't produce any noise. This means having very large and long ports, which wouldn't fit in most speakers. The drawback is it pushes down the resonant frequency of the port, which ideally should be outside the passband of that driver. Having low crossover points helps get around this. The speakers are separate cabinets which got stacked on top of each other. The cabinets are made of MDF, with the front baffle being 1.5 inches thick, and the rest being 3/4 inch, with lots of bracing. The cabinets were loosely stuffed with rock wool and polyester. One of the challenges of designing flush-mounted systems is having that speaker be built into the wall while having the speaker be decoupled from the wall, so it's not transmitting energy into the structure through the wall. You want the resonant frequency of the decoupling system to be at least half the lowest frequencies the speakers will play. That's not too difficult to achieve, but at the same time, you want a very rigid system that isn't squishy, so that when the woofers are moving, they don't make the speakers rock back and forth. In order to get a rigid system with a lower resonant frequency, you need a lot of mass or tension, which is why companies like Northwood Acoustics will use opposing steel cables with thousands of pounds of force. In my case, the speakers were heavy enough that I didn't need to worry about that. In order to design the decoupling system, I needed to have a pretty exact estimate of how much the speakers weighed, which ended up being roughly 520 kilos per side. From there, I used some simulation software to find out at which point under the speaker the load could be equally distributed on 3 points. And then I used silomer pads at those points, rated for the correct weight. Theoretically, the resonant frequency is below 10 Hz, so energy below 20 Hz or so doesn't transmit from the speakers down into the floor and the rest of the structure. Each side has a small rack of electronics used to power the speakers. I use what I call fully digital monitoring, which means I go digitally into every speaker, which then has DSP for all of the crossover and filtering required, and then there's a DAC channel for each driver, which then goes into an amplifier channel for each driver. There's nothing else in the signal path. For the entire Atmos system, this means there are 40 channels of DACs and amps. Not only does this reduce distortion by having fewer things in the signal path, and not having drivers affect each other by sharing an amp, but it allows me to correct the phase response, which is only possible with DSP. This is similar to what systems like DEX, Trinov, and Dirac do. Without phase correction, your speakers play different frequencies at different points in time. It'll play the high frequencies and then the low frequencies. This comes from the phase shift caused by the crossover filters. Phase correction allows you to delay some frequencies so that the speaker ends up playing all frequencies at the same time. Not only does this improve the detail and soundstage, but it allows you to use different speakers for an Atmos system and not have phase problems. For the main speakers, I go AES into a mini DSP flex unit with the digital I/O option. That flex handles the crossover filters and phase correction. It then goes to an Eversolo DAC for the upper 2 channels, and that goes to a topping LA90 amp. For the 2 subs, the mini DSP goes to a Geshelli J2 DAC, and then a pair of 400 watt Purify amps. The LFE subs get fed by a different mini DSP unit, and those each have a 500 watt Hypax amp. There's a total of around 10,000 watts of amps for the entire Atmos system. The center channel is similar to the stereo in having the beryllium compression driver and 8-inch mids, but it only has a single 15-inch sub, so I don't have it extending quite as low as the stereo speakers. Let's get into designing the other speakers for the Atmos system. The size of the space created some challenges, especially since I wanted to meet or exceed the Dolby specs, which most systems don't do. The rear speakers are around 4 meters away from me, which requires quite a bit of output power if you want to get down to 40 Hz with 100 dB SPL. The easiest solution would have been to either build large speakers with 12-inch woofers similar to the Strauss midfields, or go with 3-ways. If I was starting from scratch again, I would have probably just gone with larger speakers, but I wanted something fairly compact. Going 3-way would have made things significantly more expensive, as I'd need the additional driver, I'd need to double the amount of DSP units, and double the amps. One of the biggest trade-offs in speaker design are the low frequency extension, the output power, and the size of the speakers. You can never have all 3, but that's exactly what I needed here. There are very few drivers which can deliver that. If it weren't for this one woofer I found, these speakers wouldn't be possible. They use an 8-inch woofer, and then have a 1-inch compression driver in a small waveguide. They ended up packing quite a punch and being able to deliver the output power needed. The height surrounds are closer to me at about 2 meters away, so they don't need quite as much output power. I would have just gone with the same design as the other surrounds, but I needed to use these in my old studio where the ceiling height was very limited, so I built these in a similar style to the PMC wafers, where they're very shallow and don't take up a lot of space. In most larger rooms, people will either use space management so that the speakers don't need to extend down to 40 Hz at high SPLs, or they won't actually meet the SPL requirements, which means some Atmos content could easily damage the speakers. The biggest problem in most Atmos systems is using different speakers around the room. Even if they're from the same manufacturer, they'll have different phase responses. This means when you have a sound panned between two speakers, some frequencies will cancel and others won't. It's like listening to stereo with a PMC speaker on one side and an ATC on the other. No one would really do that. By having a fully digital monitoring system with phase correction, I'm able to have all the speakers have the same phase response, so I don't have any issues panning between them. The system in this room turned out better than I could have hoped for. While I will continue to experiment with different speaker designs, I don't feel a need to improve from where I am now. I'm sure this room will change in the future, but this starting point is already at a place where the room and the speakers no longer get in the way of music. It's a space where I can sit down and instantly connect. Thanks for joining me on this journey. Whether you've followed along the entire process from when this was nothing but an empty piece of land, or if you're just tuning in and watching this series. If you'd like to keep up with what I'm working on, check out my Instagram or the blog on my website. Lots planned.